here's a nice application of projections, and it's a physics example. So I've got a 100-pound object that's lying on this ramp, and we're asked to find the vector components of the force of gravity that are parallel and perpendicular to the ramp. So of course the force of gravity is going to be acting straight down. And the magnitude of the force of gravity is just the weight of the object. So I can call this vector F here for the force of gravity, and that's just going to be 0, negative 100. All of the magnitude comes from the y component, which is acting straight down. All right, what we're asked to do is basically break that force up so that rather than just writing it as pointing straight down, I want to write it as a sum of vectors parallel to the ramp and perpendicular to the ramp. So that essentially the force vector that I have becomes the hypotenuse of this right triangle, where one of the legs is parallel to the ramp and the other leg is perpendicular to the ramp. All right. This is one place where those of you who've had physics may be at a slight disadvantage. Usually that helps you out in this class. But here, in physics, you might be used to doing the problem a little bit differently. Okay, so let's look very carefully at the directions. I ask for the vector components of force. That means I do not want just the magnitudes. I don't want just the amounts of force. Those I could get just using right triangle trigonometry. I could find the length of these sides using right triangle trigonometry, but that would give me numbers. I want vectors. And then I say, don't rotate the axes. Very often what's done in physics, and it's a great thing to do, rather than saying, okay, let's let this be the x-axis and this be the y-axis, let's let this be the x prime axis and this be the y prime axis. Let's just make our axes so that they are parallel and perpendicular to the ramp. That just makes things very easy to work with for a problem like this. It's a great technique. I have nothing wrong with that technique. It's just not what we're doing. Because there are times when it can be very, very useful to rotate the axes to fit the particular problem that you're working with. But there are other times when you actually don't want to do that. If I want to know what direction the object is actually moving in, I don't want to rotate the axes to change what that direction is. And there could be a time where I've got another force that's acting in a different direction, and I can't rotate the axes more than one way. So working with a fixed frame of reference is a useful skill. Being able to rotate that frame of reference is a different useful skill. We're going to do this one without rotating the axes. Okay, so I'm going to just draw a slightly bigger picture of here's my force, and I'm trying to break it up into two vectors that look something like this, where these will be perpendicular. This vector is going to be P. That's going to be my projection onto the ramp. So I'm going to need to find a vector that's parallel to the ramp that I could project onto. So I'm going to do that. If I started here at the top of the ramp and I went down 3 and over 5, that would take me to here. There I would be writing essentially the ramp as a vector pointing from the upper left-hand corner to the lower right-hand corner of the ramp. Notice that would have me going 5 over and 3 down. Do be careful that the horizontal component is in x and the vertical component is in y, and it's not 5, 3, it's 5, negative 3, because I'd be going down and to the right. If you wanted your vector parallel to the ramp to be pointing up the ramp, you could certainly do that. Then you'd be going left 5, so you'd have a negative 5, and up 3, so this would be a positive 3. Does not matter which direction we go. I've chosen the direction so that now my projection will actually be a positive multiple of this ramp vector, because the ramp vector I've chosen is going right and down, and that's the direction that this projection is going to be going as well. But it doesn't matter. If you chose to be going up and to the left, you would just get a negative multiple of that ramp vector. All right, excellent. So there's my ramp vector. Now, if I wanted to, I could normalize that to get a unit vector. I think I'm just going to work with it as is. And so I just have to remember to use the formula for projecting onto an arbitrary vector. So P, which is the projection of F onto the ramp. I know that's going to be a multiple of the ramp vector, because the ramp vector gives me the right direction. The scalar that I'm going to multiply that by will be f dotted with r. I dot the two vectors, the one that I'm projecting and the one I'm projecting it onto, divided by the magnitude of r squared. Or if I prefer, I could write this as r dotted with r. In fact, I think I'm going to actually write it that way because that's how I'm going to work it out. Okay, so f we said was 0, negative 100. We're dotting that with 5, negative 3. On bottom, we'll have 5, negative 3 dotted with itself. And that, all of that is the scalar by which I'm going to scale my vector r, which is 5, negative 3. Okay, so let's work out those dot products. So I'm just working out what this scalar is now. Here, my first components are just going to give me 0, and then negative 100 times negative 3 will give me positive 300. On bottom, 5 times 5 is 25, plus negative 3 times negative 3 is 9, so I'm getting 25 plus 9, that's going to be 34. All right, I can reduce that. That's going to be 150 seventeenths, and it's times 5, negative 3. I'm going to go ahead and do that scalar multiplication. So that's just going to give me, let's see, 750 seventeenths, comma, negative 450 seventeenths. Okay, now that's my projection onto the ramp. At this point, I like to do just a quick common sense check. Looking at this, I can see the x component is positive and the y component is negative. So we're going right and down. Yep, that's what we're supposed to do. But I could catch a careless error fairly easily if I had a negative component here or a positive component here. I'd know it was going in the wrong direction. So this doesn't guarantee that I haven't made a careless error somewhere else, but at least it does catch some careless errors. All right, so I can say that P is the component parallel to the ramp. And we've just calculated that. That's our 750 seventeenths, comma, negative 450 seventeenths. And this is a force vector, so the units for it would be pounds because that was the unit of weight or the unit for the force of gravity that we were using. All right, I want to find the other component as well. And so I could, if I really wanted to, find a vector that's perpendicular to the ramp and project onto that. That would be a lot of work. What's a whole lot simpler is to say that, hey, this vector plus this vector has to equal the original force vector. So if I solve for this, it's just going to be F minus P. That way P plus F minus P is going to equal F. So I can just use vector subtraction to find the component that's perpendicular to the ramp. So F minus P is the component perpendicular to the ramp. And we can work that out. So that's 0, negative 100 minus 750 seventeenths, negative 450 seventeenths. Okay. So let's see, 0 minus 750 seventeenths is going to be negative 750 seventeenths. For this component, I'm going to rewrite that negative 100 as negative 1700 seventeenths, and then I'm subtracting a negative, so I'm going to add 450 seventeenths to that. And so let's see, what does that give me? That's going to give me negative 1250 seventeenths. Excellent. Let's again do a quick common sense check. Negative and negative has me going left and down. And if I look at the picture, this vector here is going left and down. So those are my vector components. This vector and this vector are the vector components of force, parallel and perpendicular to the ramp.